Hello, Course. I'm recording this video for anyone who was not able to join us earlier during our Google Meets, so you can catch up with us. Today we looked at a slideshow about the atmosphere presented by Kessler Science. This slideshow is going to review some of the concepts we went over last week, as well as introduce a few new ones that we'll need going into the rest of the week. So it's important that you keep up with me this week. So Kessler Science made our PowerPoint that we used. And earlier today, everyone worked on some guided notes together in Kami. I'm going to show you what that looks like. So everyone online today, everyone remote, worked on these notes together, what you're seeing here. All the different colors of writing are different people who were working to edit the same document. I'm going to edit this document tomorrow and make sure that things are correct and then give it back to you tomorrow afternoon. But if you see anything that's incorrect on this document while we are working on the slideshow, you can click on that first link in that Canvas, in the Canvas module, you can click on the first link and get here, and you can change that if you would like to. Okay, guys. So, switching back over to here, I want to show you guys, if you would like to see the slideshow, you can either look at the slideshow here, or you can also click on this second link to be able to see it. The slides that you are responsible for viewing today is slides 1 through 9. There are no other assignments today, so just watch along with me through slides 1 through 9. Okay. So I'm going to switch over to this slideshow now. We're going to go through it together. So first thing I would like you to do if you're totally remote is please make a new bell ringer sheet. We had one from last week, but you can put that one up and use a new one. So this new one, please title today as 0914, and we're going to start working there. So first I want you to take a look at these essential questions. Our first essential question is, what is the composition of the Earth's atmosphere? And our second essential question is, what are the layers of the Earth's atmosphere? So first thing I want you to answer on your bell ringer sheet is number 1, if you were quizzed today, which questions would you already know the answer to? And then number 2 is, which questions would you need to learn more about to answer confidently? It's okay if you answer both questions for these spots or if you just answer one. I'm going to give you, please pause the video now and go ahead and write your response. Okay, now on to our next page. So we know that the atmosphere is a thin layer of gases that surround the Earth. The purpose of our atmosphere is to support life on Earth by protecting it from dangerous electromagnetic radiation, or the sun's rays. We talked a lot about this one last week. The electromagnetic radiation is the rays from the sun. The second thing is to create and control weather and climate. And our third thing is to provide gases to plants and animals that they need to breathe. So I want you guys to pause the video again here, and on your bell ringer sheet, please write the definition to atmosphere, or a definition to atmosphere. I want you to write this definition in your own words. So write a definition like it would appear in the dictionary using your own words. Go ahead and pause the video now to complete that. Okay, guys, the next thing we're going to talk about is the composition of the atmosphere. So 2 observations I think you should make right off the bat is that nitrogen makes up a lot of our atmosphere. And it's a very important element like we talked about last week. Nitrogen is a basic building block for life. We also have a lot of oxygen in our atmosphere, but nitrogen helps dilute that oxygen in order for us to breathe. We're able to breathe it because nitrogen dilutes that oxygen. Some other elements we may find are argon and carbon dioxide, as well as other trace gases such as neon, methane, krypton, and hydrogen. Now, a fun fact, and something we'll take a look at more next week, is if you look here at this 0.90, these are significant figures. So when we write 0.90, we're wanting our audience to know that we are being precise about this number, that there is precisely 9/10 and 0/100 of argon in the atmosphere. And it's important that we write that 0.90 instead of writing it as 0.9. These are also significant figures on carbon dioxide. We have a 0.03. That's showing us that there is 3/100 of carbon dioxide in our atmosphere. Okay, guys, so let's talk about these gases and why they're important to us. Nitrogen is removed from the atmosphere by bacteria, which needs it to function. It needs it for its DNA. And lightning, which heats up the ground and kind of sucks nitrogen up from it. And those are just two examples. Nitrogen compounds are used by plants in growth and development. So if any of you have ever fertilized a plant before, you are adding nitrogen to that plant to help it grow. Water vapor, or H2O, has different amounts varying in the atmosphere, so it's always changing. It's never the same or static. It cycles through the hydrological water cycle, which I know you guys talked about last year in 6th grade, but we're going to talk again some more this year. Earlier, I got a great question about why there's a 2 here. So the reason you see a 2 is because there are 2 hydrogens and 1 oxygen in a water molecule. So we breathe in oxygen and we emit carbon dioxide. When we breathe in, we breathe out carbon dioxide. This carbon dioxide is removed from our atmosphere by green plants. Any carbon dioxide is, not just ours. And then that plant releases oxygen back into the atmosphere through photosynthesis. Okay, the next thing I want to talk about is atmospheric pressure. So if you see here, these are the different layers we learned about last week. We have the troposphere, the tropopause, which I don't expect you guys to know about the tropopause, but you might want to know it in case there's extra credit on a quiz or a test. So we have the troposphere, the tropopause, the stratosphere, the ozone layer, which is inside of our stratosphere. We have a mesosphere, a thermosphere, and then right above it, the exosphere. Think about it this way. Down at the troposphere, the Earth is closest to it. And so it's able to get the best grip on the troposphere. The Earth's gravity is able to get the best grip to pull down on the troposphere. That means there's a lot of pressure being exhibited on this troposphere, or there's a lot of pressure being put on this troposphere. Up here at the top with this thermosphere, there is less pressure on it, and it's farther away, so the Earth's gravity is not able to get as strong of a pull on it. So as we increase in altitude, our pressure decreases. And if you look over here, this is a square inch. It has 1 inch on both sides, so it's a square inch. And down here at sea level, that little square inch has 14.7 pounds of pressure being put on it. That's a lot of pressure. So the closer you get to sea level, to Earth, the more pressure is being put on our atmosphere. So this one's one of the most important. If you remember anything about today's lecture, please remember this part. So, at greater altitudes, the same volume contains fewer molecules of gases. So down here at the very bottom near Earth, this is like our troposphere and our stratosphere. There is a lot of these molecules, and they're constantly moving around and hitting each other. Constant movement. In the very middle, mesosphere, there's not as many molecules anymore, but there's still a few of them. There's still plenty of them, and they still may hit each other occasionally. And then up here at the top, there is very few molecules. So unlike the others, we don't see as much density. There's not as much density. So down here at the bottom, more density. Up at the top near the thermosphere and especially the exosphere, there's not as much density. You guys can kind of remember this by thinking about population density. So if you think of the troposphere, the molecules, kind of like people in Raleigh. There's a lot of people in Raleigh. You can't go anywhere without seeing people in cars. And that's kind of like the molecules in the troposphere. There's a lot of molecules here. It's very dense. In the middle, you can think of this kind of like Winston-Salem or Greensboro. There is still enough people that you see them, but it's not so densely packed. There's not as many. So this is less dense than the troposphere. And as we get to the very top near our thermosphere and exosphere, you can think of this almost like Randleman. So if you've ever been driving at night, you may not see another car in Randleman while you're driving, but you still know there's people around. And so that's kind of like the thermosphere. There's still molecules, but there's not as many of them. So it is the least dense of all of these. And this density is measured by a barometer, which is over here, which uses mercury and pressure to gauge how much pressure is being put on these different layers of our atmosphere. So the last thing I want to talk to you about is atmospheric warming through solar radiation. So solar radiation is another instance where you can have too much of a good thing. We often hear about solar radiation as being the bad guy that is causing global warming, and it has a lot to do with that, but we do need a certain amount of it, and in certain amounts, solar radiation is healthy. So 49% of solar radiation is absorbed by Earth's surface. So if you've ever stepped on the pavement on a hot summer day, it kind of burns. It's very warm. It's very hot. And this is because the ground is taking in that solar radiation and keeping it, and it's warming the surface. This radiation is also taken in by plants and trees, vegetables, different crops, and us, and many other things. 20% of the solar radiation is reflected off of the backs of clouds. So it hits the back of a cloud and it's reflected back up into space. 20% more is absorbed by our atmosphere in the clouds. So if you think about when it thunderstorms outside, sometimes the clouds look like almost like they're glowing, like they're fluorescent. And this is the energy that they have absorbed. 6% is scattered into our atmosphere. There's many ways that this shows up to us, but in one way it can be the light that hits the water molecules that show up in a rainbow. And then 5% is reflected by Earth's surface. So 5% of the solar radiation hits Earth's surface and then shoots back up into space. So I want us to go over these questions today. Please pause the video here and take some time to look at these questions and think of the answers yourself, and then we'll talk about it. Okay, guys, so number 1, is air matter? Air is matter. So there's 3 different forms of matter. There is solids, liquids, and gases. Air is a form of gas. It is gas. It is a gas, so it is matter. Air also has mass. There is a mass to air. A lot of time we think of air as being weightless, but that's not necessarily true. It's a misconception. Air does have mass, and we know that it has mass because there can be different amounts of pressure exerted at different altitudes. So air does have mass. Our ears pop when we're flying or going up a mountain because we're going from a lower place in elevation to a higher place in elevation. And the lower place in elevation has a greater pressure being put on us. So if we're in the foothills of North Carolina, there's a lot of pressure being put on us by the atmosphere. But when we go up the mountain, there is less pressure being put on us. And so our ears pop to relieve this pressure. And finally, number 5, it is not recommended for us to scuba dive in the morning and then fly home that same afternoon because you're going from a lower place in altitude with greater pressure to a higher place with less pressure. And this can cause us to get altitude sickness sometimes. This can kind of make us dizzy because of this change in pressure and density. Okay, you guys, that's all I had for us to do today. We're going to go over the rest of this PowerPoint tomorrow, so please make sure that you're available for that. And I can't wait to see you there. Have a good night.